Okay, so let's talk about one of the things that gives chemistry students nightmares, naming organic molecules. I mean, take a look at this thing. It looks like a total mess of lines and letters, doesn't it? But what if I told you there's a simple, totally logical system behind it, a kind of blueprint, if you will?
Seriously, where do you even start with something like this? It's like someone's asking you to read a language you've never even seen before. But here's the secret. It is not about memorizing a million different rules. It's about understanding a really simple, elegant system, a kind of chemical grammar. And once you learn the rules of that grammar, you can name pretty much any molecule you see.
And here is that grammar in action. Just look at 6-methyloctan-3-ol on the screen. The suffix, that ol, that's like the verb, it tells you the most important thing happening in the molecule, that it's an alcohol. The root, octan, well, that's the noun, telling you the main carbon chain has 8 carbons. And then you have the prefixes, like 6-methyl. Those are just the adjectives, describing all the extra bits and pieces. See? It's a language, and today we're going to get fluent. So how do we actually master this chemical language? Not by flipping through some giant, dusty textbook. Nope. We're going to do it with a simple 4-step blueprint. And this blueprint is your key to cracking the code of any organic molecule out there. Here it is. This is our roadmap. First, the anchor. We find the most important part of the molecule. Second, the foundation. We map out the main carbon skeleton. Third, the grid. We lay down a numbering system. And finally, step 4, the assembly. We put all the pieces together to build the perfect name. So, let's dive in. All right, first things first, and this is maybe the most important step, we gotta figure out who's the boss. You see, every molecule has what's called a principal functional group that basically dictates its entire identity. This is the most important part, the one that gets top billing and defines what the molecule really is. And how do we find this boss? With these 2 powerhouse tools you see on your screen. First, you look to the priorities staircase on the left. Think of it like a corporate ladder for chemicals, seriously. Way up at the top, you've got the CEOs, the carboxylic acids, and way down at the bottom, you have the interns, the alkenes. Now, if a molecule has a bunch of different groups, the one that's highest on this staircase always wins. It's the law. Once you've found your winner, you look to the diagnostic matrix on the right. This tells you exactly what to call it. If it's the boss, you use its suffix name. But if it lost the fight for the top spot, it's a subordinate, and you have to use its prefix name. It really is that simple.
Okay, so we've crowned our boss. Now it's time to build the framework around it. Steps 2 and 3 are all about finding the longest carbon chain that actually includes our boss, and then numbering it correctly. This gives us our foundation and our grid.
And this slide right here shows the absolute golden rule of numbering, the lowest locant rule. Now, a locant is just a fancy word for the number we assign to a carbon. It's like its address on the chain. Look at the molecule on the screen. We could number it from right to left, that's path A, which puts our boss alcohol group on carbon number 6. Or we could go left to right, path B, which puts it on carbon 3. Well, the rule is simple and it is absolute. The boss gets the lowest number possible. 3 beats 6 every time, so path B is the one and only correct way. So we've found our boss, we've built the foundation, and we've laid out the grid. Now, for the really fun part. Let's put all the pieces together and see this blueprint in action. Now, this is where the system really shines, handling conflict. This molecule has both a carboxylic acid and a ketone group. So who wins? We go right back to our priority staircase. The carboxylic acid is way, way higher up, so it claims the suffix, oic acid. The poor ketone gets demoted. It becomes a subordinate, so it has to use its prefix, which is oxo. The result? 5-oxohexanoic acid. The hierarchy resolves the conflict perfectly, every single time.
Oh, this is a fantastic comparison. Look at molecule A on the left. It's a battle between an aldehyde and an alcohol. You check the staircase, aldehyde wins. It gets the suffix ale, and the alcohol gets demoted to the prefix 6-hydroxy. Now look over at molecule B. The structure's pretty similar, right? But we've swapped into ketone. Now it's ketone versus alcohol, and the ketone is higher on the staircase, so it wins, claiming the suffix 1. The structure defines the priority, and the priority dictates the name. The blueprint is flawless.
You know, the system is so precise, it even has built-in rules for spelling. So here, we have 2 of the exact same ketone groups, so we use a multiplier, di, to make the suffix dione. Simple enough? But notice how we keep the E on hexane? That's because the suffix dione starts with a consonant. If the suffix started with a vowel, something like all, we'd drop that E. It's these amazing little details that make this chemical language so powerful and so unambiguous. Okay, but what about a really complex chain with both double and triple bonds? Yep, the blueprint has it covered. We've got a 6-carbon chain, so hexa. 2 double bonds give us a diene, and 1 triple bond gives us an ine. The role here is to number the chain to give the lowest possible set of numbers to all of those multiple bonds. In this case, numbering from either side gives us the set 1, 3, and 5. It's a tie. So what do? Well, in a tie, the double bond gets the lower number, so we number from the left, which gives us hexa 1,3-diene 5-ine. See, the system is incredibly robust.
So, we've gone from the structure to the name, but the real test of fluency, the true sign of mastery, is going the other way, reading the name and drawing the molecule. Let's try to reverse engineer the blueprint.
And here's the trick. When you draw a structure from a name, you work backwards. You build it from right to left. Let's try to build pents 4-in-2 all together. We start with the suffix, main-2-all. That's our anchor. We know we have an alcohol group on carbon number 2. Next, the root, pent 4-ene. That's our foundation. Pent means a 5-carbon chain, and 4-ene tells us there's a double bond at position 4, so we draw that out. Any prefixes? Nope. And we're done. You just built the entire molecule piece by piece just by reading the blueprint in reverse. So let's just recap the entire blueprint one last time. It really is just 4 simple steps. 1, find the boss using the priority staircase. 2, find the longest carbon chain that actually contains that boss. 3, number that chain using the lowest locant rule. And 4, name and assemble all the other little pieces as prefixes, putting them in alphabetical order. That's it. That is your master algorithm. We started with a molecule that looked just impossibly complex, right? But now you have the code. You have the grammatical rules to not only read chemical structures, but to write them yourself. You have the blueprint. So the only question left is, what are you going to build with it?